students, welcome to Sunil's tutorial. I'm Sunil Nirwani and today we'll be doing rice cheese experiment. Let's see this. Please draw this diagram, guys. Done. Right, apparatus. Let's see the apparatus. Very simple, straightforward apparatus. Right, the apparatus consists of a U-tube manometer. The apparatus consists of a U-tube manometer whose two arms are closed, by two coaxial cylinders P and Q. Whose two arms are closed by two coaxial cylinders P and Q. A third cylinder R is placed coaxially between P and Q. Cylinder R is filled with hot water. And can be rotated. Cylinder R is filled with hot water and can be rotated about a vertical axis. One face of each cylinder P, Q and R is coated with lamp black. One face of each cylinder P, Q and R is coated with lamp black while the other is kept polished. Guys, look at this. This is your U-shaped manometer. The arms are closed with this coaxial tube. You have this third coaxial tube. All of them are in the same line. One face of each of the cylinders coated with lamp black. So that's your apparatus. Let's see the experiment. Right, experiment. Initially P, Q and R. Initially P, Q and R are all at the same temperature. Initially P, Q and R are all at the same temperature. The temperature of R is raised. The temperature of R is raised by pouring hot water in it. The temperature of R is raised by pouring hot water in it. Now guys, if I raise the temperature of R by pouring hot water in it, what will happen? It will start giving radiant energy, and the radiant energy is going to be given out by both the faces. So radiant energy is going to be absorbed by this cylinder P as well as Q. Right, let's write that down. The radiant energy given out, the radiant energy given out by both faces of R is absorbed either in part or in whole, by the faces of cylinder P and Q. Now guys, let's see the experiment. You put hot water into this. This gives out heat energy. Heat energy is absorbed by both the faces, either in part or whole. As the heat energy here increases, in P increases, it will expand the air inside and will exert a pressure on the liquid inside. Similarly, this has also absorbed heat energy, so therefore the air inside will expand. That will also exert a pressure on the liquid column in the U tube. What we see is that the liquid column in the U tube remains same in both the columns. That means the pressure exerted by P is equal to the pressure exerted by Q. That is the reason why the liquid column remains same in both the arms of the U tube manometer. Let's write this down. Due to the energy absorbed, due to the energy absorbed by cylinders P and Q, due to the energy absorbed by cylinders P and Q, the air in these cylinders gets heated. The air in these cylinders gets heated and expands, and hence exerts a pressure on the manometric liquid. When the black faces of all the cylinders, when the black faces of all the cylinders are in the same direction, the liquid level in manometer are equal. The liquid level in manometer are equal. This shows that both cylinders P and Q, this shows that both cylinders P and Q absorb equal quantity. Both cylinders P and Q absorb equal quantities of radiant energy per second. Let's assume that A is the cross-section area of each cylinder. Small a is the coefficient of absorption. Of the polished face. E is the coefficient of emission of the polished face. Capital E is the emissive power of the polished face of the cylinders. And EB is the emissive power of the black face. Now in this case, guys, the radiant energy, guys, write it down. The radiant energy emitted per second by the black face of cylinder R. How much will be the radiant energy emitted? That will depend upon, since it is black face, so emissive power of the black face and total energy. See, emissive power is the energy per unit area multiplied by the total area. That will tell you how much is the total energy emitted by the black face of R. EB will tell you how much is the heat energy emitted per unit area per second, per unit time. Since I want to know the total energy emitted per second, I multiply by the area. Now, if you look at the diagram, this energy is incident on the polished face of P. This energy is incident on the polished face of P, right? This energy is incident on the polished face of P, and it absorbs, since it is polished face and not a black body, it will absorb only a part of it. So it will absorb whatever is its coefficient of absorption into the total energy. So this is the total energy that is absorbed by the polished face of P, right? I can say this energy is also incident.
Why EB?
Because area into EB. This was the energy. This is the total energy that is
Yeah.
incident on the polished face, multiplied by the coefficient of absorption will tell you how much cylinder P has absorbed, right? This energy is also incident on the black face of cylinder Q. Now, if it is incident on black face of cylinder Q, for a perfectly black body, the coefficient of absorption is 1. That means the entire energy is going to be absorbed by is going to be absorbed by Q. Hence, it absorbs A into EB. The coefficient of absorption for a black body is 1. So 1 into A into EB, that's A into EB, because that's a black body. We have coated one face with lamp black. Now, since the liquid level is same in the two arms, the liquid level is the same in two arms. That means the heat energy absorbed by P should be equal to the heat energy absorbed by Q, because both of them are expanding air to the same extent and exerting same pressure. That means I can therefore say that A into EB is A into E, right? This is going to be not EB but A into E. That's your emissive power of the polished body, right? So in that case, guys, just make this correction. This is A into E, because this is going to be from the polished side, right? So the polished surface is going to emit so much heat multiplied by the area. This is the amount of heat emitted per unit area multiplied by the area. So in that case, A and A gets cancelled. So I'll get A is equal to E upon EB, right? And this verifies Kirchhoff's law. Next, let's try to see Stephen's law. Let's write the law down first, then I'll explain the law. Now, according to Stephen's law, the radiant energy emitted per unit time, per unit area of a perfectly black body is directly proportional to the fourth power of its absolute temperature. That is what is Stephen's law. The radiant energy emitted per unit time per unit area of a perfectly black body is directly proportional to the fourth power of its absolute temperature. Now guys, let's assume that if Q is the quantity of radiant energy emitted per unit area per unit time, and T is the absolute temperature of the body, then as per Stephen's law, Q is directly proportional to the fourth power of absolute temperature. That is what is Stephen's law. That heat is directly proportional to the fourth power of absolute temperature. Therefore, I can say that Q is equal to sigma times T4, right? Where sigma is called as Stephen's constant. Where sigma is Stephen's constant, right? The value of sigma is found out as 5.67 into 10 raised to minus 8 joules per meter square second Kelvin 4. So do we understand Stephen's law? Next, let's see this. Let's see how do I apply Stephen's law to net loss of heat. Stephen's law to net loss of heat. Let us consider, guys, that there is a perfectly black body at absolute temperature T. There is a perfectly black body at absolute temperature T surrounded by another black body at absolute temperature T0. Both are perfectly black body. This is at absolute temperature T, this is at absolute temperature T0. Right? Let us also consider that A is the area of the inner body. Right? Let's write that down first. Consider a perfectly black body at absolute temperature T surrounded by another perfectly black body at temperature T0, absolute temperature T0. Let's assume that A is the area of the inner black body. Let A be area of inner black body. Now, since the inner black body is at a higher temperature, it is going to the inner black body loses heat energy at sigma into T4 as per Stephen's law. I can say that the inner black body loses heat energy sigma T4 per unit time. This is the amount of heat energy it is going to lose. It is also going to receive heat energy because every body continuously loses as well as receives heat energy. It also receives heat energy. It is going to receive heat energy from the outer body. So how much heat energy will it receive? Sigma T04 per unit time. Since T is going to be T is greater than T0, therefore it will lose more energy and gain less energy. Hence there is going to be a net loss of energy. I can say hence net loss of energy is going to be sigma T4 minus sigma T04. which is equal to sigma T4 minus T04. But for a perfectly black body, the total heat is absorbed. That means I can say for a perfectly black body, Q is equal to EB. Right? Now, in that case, I can say that Q, we had already said that Q is equal to sigma T4, but Q is equal to sigma T4. Therefore, I can say that EB is sigma T4. I could also say coefficient of emission is nothing but emissive power of the body to the emissive power of a perfectly black body. Therefore, I can say that E is emissive power of the body into emissive power of a perfectly black body. Right? Now, we already found out, guys, see this. We already found out the value of EB. We already found out the value of EB to be sigma T4. Substitute this value of EB in the above equation. So in that case, I'll get E is equal to E into sigma T4. So emissive power of the body is coefficient of emission into Stephen's constant into fourth power of absolute temperature, right? So that is your equation for loss of heat per unit. This is your the above relation gives you the emitted energy emitted per unit time per unit area, and that is also your equation for net loss of heat per unit area per unit time. Right? So that means I can say that this is your loss of heat per unit area per unit time, and this is also your net loss of heat per unit area per unit time. Fine, do we get this thing clear? Next, let's derive Newton's law of cooling. Let's first write Newton's law of cooling. Newton's law of cooling states that the rate of loss of heat by a body is directly proportional to the excess temperature of the body over the surrounding. Provided that the excess is small. So your Newton's law of cooling states that the rate of loss of heat of a body is directly proportional to the excess temperature of the body over the surrounding, provided the excess is small. Let us assume, I'll explain this law with the equation, that theta and theta 0 be the temperatures of the body and the surrounding. Be the temperature of the body and the surrounding. Right? In that case, the rate of loss of heat by a body will be nothing but rate of loss of heat will be rate means d by dt, heat means q. So rate of loss of heat will be nothing but dq by dt. By Newton's law, what does he say? He says that the rate of loss of heat is directly proportional to the excess temperature of the body over the surrounding. So dq by dt is directly proportional to theta minus theta 0. Therefore, I can say that dq by dt is equal to k times theta minus theta 0, where k is the constant of proportionality. Now let us assume that m is the mass of the body and s is the specific heat. Let m and s be the mass and specific heat of the body. In that case, we know that rate of loss of heat of a body is also given by mass into specific heat into fall in temperature. You learned this in school. Q is equal to mct. Heat is equal to mass into specific heat into change in temperature. So therefore I can say that rate, instead of Q is equal to mct, I am putting rate on this side and I am putting rate on the other side. Right? Same formula I am using. Therefore I can say that dq by dt is equal to ms d theta by dt, where theta is the change in temperature. Right? But by Newton's law, guys, by Newton's law, dq by dt is k theta minus theta 0. Therefore, I can say that k theta minus theta 0 is equal to ms d theta by dt. Right? In that case, I can therefore say that d theta by dt is nothing but k upon ms into theta minus theta 0. So this is how you derive Newton's law of cooling. Right? So Newton's law of cooling says that the rate of fall in temperature is directly proportional, this is your constant, directly proportional to the excess temperature of the body over its surrounding. Right? Now let us try to derive Newton's law again by using Stephen's law. Derive Newton's law using Stephen's law. Let us consider a perfectly black body at absolute temperature T with surface area A. Consider a perfectly black body at temperature T and area A, where A is its surface area. Let us assume that T0 is the absolute temperature of the surrounding. Let T0 be absolute temperature of surrounding. Right? Now, by Stephen's law, if I apply Stephen's law, Stephen's law states that the rate of loss of heat per unit area, rate of loss of heat is nothing but sigma T4 minus T04. Right? This is per unit area, and for total area A, Therefore I can say that rate of loss of heat, this is rate of loss of heat per unit area. Therefore the total rate of loss of heat is going to be sigma into A T4 minus T04. If per unit area it is this much, multiply that by area, that will give you the total loss of heat, right? And that means I can therefore say that the change of heat, rate of loss means the change of heat with time. Therefore you could say that dq by dt is equal to sigma A T4 minus T04. Now let us assume, let x denote the excess temperature of the surrounding. That means I can therefore say that T is equal to T0 plus X. The temperature of the body is nothing but the temperature of the surrounding plus excess temperature. Substitute this value in the equation. If I substitute this, I'll get dq by dt is sigma A. Instead of T, I can write T0 plus X the whole raised to 4 minus T0 the whole raised to 4. This can be written as sigma into A. Guys, observe very carefully. I'm going to multiply by T0, I'm going to divide by T0. So I'm multiplying by T0, I'm dividing by T0. The whole raised to 4. I'm multiplying by T0, I'm dividing by T0, right? Minus T0 the whole raised to 4, I can do that. In which case, I will get this as sigma A T0 the whole raised to 4 1 plus x upon T0 the whole raised to 4 minus T0 raised to 4. Now in the expansion of this, of 1 plus x upon T0 the whole raised to 4, the first term will be x. By binomial expansion, the second term will be 4x upon T0, and the subsequent terms will contain higher powers of x upon T0 plus higher powers of x upon T0. But x is nothing but the small excess of temperature over the surrounding. That means x upon T0 is going to be less than 1. But x upon T0 is less than 1. That means the higher powers of x upon T0 will approximately be equal to 0. Therefore, higher powers of x upon T0 will approximately be equal to 0. When you do binomial expansion, 1 plus x upon T0, you have first term, n time the second term, and then you will have powers of it, square, cube, raised to 4, right? Now, this is okay. X upon T0. Now, if I take square of x upon T0, I will get a number which will be smaller than x upon T0. If I take cube of it, I will get still smaller number. Now, x upon T0 in itself is a very small number. If I square it, I will get a number which is approximately equal to 0. Similarly, when I cube it, I will again get a number which is approximately equal to 0. Right? So, all the higher powers of x upon T0 will approximately be equal to 0. In which case, I can therefore say that 1 plus x upon T0 the whole raised to 4 is approximately equal to 1 plus 4x upon T0, right? Substitute this value in the equation. If I substitute the value in the equation, I'll get dq by dt is sigma A T0 the whole raised to 4, 1 plus 4x upon T0 minus T0 the whole raised to 4. I substituted the value of 1 plus x upon T0 the whole raised to 4. Now open the brackets and simplify. This is sigma A, this is T0 the whole raised to 4 plus T0 the whole raised to 4 into 4x upon T0 minus T0 the whole raised to 4 plus T0 the whole raised to 4 and minus T0 the whole raised to 4 gets cancelled. So this is sigma A 4x upon T0 the whole raised to q. Sorry, in T0 it should be in the numerator. T0 q into 4x. Fine, do we get this thing here? Now, x can be substituted as t minus T0. Now I could say that this is nothing but 4 sigma A T0 the whole cube into x. If I rearrange this, 4 is constant, sigma is constant, A is constant, temperature of the surrounding is constant. That means I can say that dq by dt is directly proportional to x. But what is x? X is nothing but the excess temperature of the body over the surrounding. Therefore, I can say dq by dt is directly proportional to t minus T0, which is similar to theta minus theta 0, right? And this is how you derive Newton's law from Stephen's law. Fine, do we get this thing clear? Next, let's see something more. Let's try to find out the solar constant. Now, what do we understand by solar constant? Solar constant is defined as, please write this down. Solar constant is defined as the amount of solar energy is defined as the amount of solar energy received per second per unit area by a perfectly black body held at right angle to the direction of the sun's rays. Held at right angle to the direction of sun's rays and placed at a mean distance of the earth from the sun, and placed at a mean distance of earth from the sun. I'll just explain this to you. In the absence of atmosphere, atmosphere. That means if I were to keep a perfectly black body exactly at perpendicular to sun's rays, if there was no atmosphere, the amount of heat that would be absorbed by a perfectly black body would be the solar constant, right? That would tell me what is the temperature of the sun. Let's try to find out the temperature of the sun. that the heat received by first of all, let's see. Let us assume that let S be the solar constant. Let us assume that S is the solar constant, and let us also assume that the heat received by unit area of a perfectly black body on the Earth's surface per second is equal to S. Heat received per unit area per unit time on Earth's surface by a perfectly black body is equal to S. Let's assume that D is the mean distance between the Earth and the Sun. Mean distance between Earth and Sun. Therefore, each meter square surface of the sphere of radius d with Sun at the center will receive a heat which will be equal to S. S is the total heat that is received. S is in that case total heat that is going to be received will be the heat received per unit time per unit area into the area, right? Will be nothing but S into area. Now area, how do I find out the area? The area of a sphere, surface area of a sphere is 4 pi r square. Here r is the distance between the Earth and the Sun, right? In that case, therefore I can say r squared. So r I am considering as the distance between the Sun and the Earth. Sun, Earth. The mean distance between them is d.
So area किसका ढूंढना है?
I am finding out what will be the area that what will be the. I am considering a sphere that will have center as the center of the Sun and radius equal to the mean distance between the Earth and the Sun. I am considering that sphere. So we are considering a sphere with center as the center of the Sun and radius equal to the mean distance between the Earth and the Sun. So what will be the total heat received in that total area? Because Earth is also a part of that total area, so I want to find out the total heat in that area. So in that case, that area is going to be 4 pi d square, in which case I can therefore say that total heat is equal to S into 4 pi d square. Right? In which case now I can therefore say, if I apply Stephen's law, I can say that Q is equal to total heat is equal to A sigma T raised to 4, assuming that the Sun is a perfectly black body with coefficient of emission as 1. Assuming Sun to be a perfectly black body with E as 1, that will be the total amount of heat, and that capital T is the absolute temperature of the Sun. So if capital T is the absolute temperature of the Sun, in that case the total amount of heat energy radiated by the Sun by Stephen's law will be nothing but A into sigma into T raised to 4. But we found out the value of A to be 4 pi d square sigma into T raised to 4. Right? We had also found out by Stephen's law that total heat, but by Stephen's law we had also found out that Q is equal to 4 pi d square into S. Right? This is also the total amount of heat, this is also total amount of heat. Therefore, I can equate the two equations. 4 pi d square sigma T raised to 4 is 4 pi d square into S. Therefore, I can say, there's some mistake somewhere, guys. Assuming the sun to be a perfectly black body, it should be, here I have to consider the total amount of heat emitted by the sun. So total amount of heat emitted by the sun, that means the radius of sun is R. Assuming the radius of sun as R. Here I was assuming the entire sphere that the sun would cover. Here I am just assuming the amount of heat emitted by the sun. The amount of heat emitted by the sun, it's spherical. So 4 pi r square will be the area of the sun, sigma T raised to 4. Right? So this is 4 pi r square, sigma T raised to 4 is 4 pi d square into S. So 4 pi and 4 pi gets cancelled, in which case I will get T raised to 4 is nothing but d square upon r square into S. And something is missing, sigma, S upon sigma. Therefore T raised to 4 is d upon r, the whole square into S upon sigma. Now we already know by experiment that the distance between the earth and the sun is 1.5 into 10 raised to 11 meters. Radius of the sun is 6.96 into 10 raised to 8 meters. Solar constant is nothing but it's a constant, 1.353 into 10 raised to 3 SI units. And sigma, we had already said, is 5.67 into 10 raised to minus 8 SI units. When I substitute all these values in the above equation, you will get the value of T to be 5770 Kelvin. Right? That is going to be the mean temperature of the sun. Fine, do we get this thing clear? We'll stop this here for the day. Thank you very much.